My name is Chengkai. I figured in this room there must be a lot of professors, and let me ask you one question. So what are the consequences of letting your student graduate before the paper is published? One of the consequences is you may end up presenting it yourself. Okay. But what are the benefits of doing that? The benefit is that if there are details that I cannot comfortably explain, or questions I cannot handle well, then I'll say, I'll ask Gensen and get back to you later. Okay. So Gensen got a great job at Google, and you have to let him go. And he has done great work. So this was mainly driven by him. So the paper is about this system called Maverick, which is a data mining system for finding, discovering exceptional facts about entities from knowledge graphs. So what do we mean by exceptional facts? Let's look at this factual statement from a news article from ABC News. Denzel Washington followed Sidney Poitier as only the second black to win the Best Actor award. So in this statement, we see several elements. Okay, one of them is an entity of interest. In this case, Denzel Washington. And there's a context. The context basically has all the Best Actor award winners. There's an attribute that we consider, in this case, ethnicity of these award winners. And then there's a peculiar value, in this case, African American, because Denzel Washington is one of the two that satisfy this peculiar value on that attribute, ethnicity. So the problem that we consider in Maverick is quite intuitive and simple. So basically, given an entity of interest, X, our goal is to find a context and a subspace of attributes such that the context has a lot of entities, right? The more the better, including the entity of interest itself. And this entity of interest bears a peculiar value that is only valid for a few in the context, including X itself, right? So that's what we mean by exceptional facts. And we can actually find examples of factual statements from real-world news articles, right? So in this slide, you see two more examples. This was Brazil's first own goal in World Cup history. Okay? Another one being Hillary Clinton becomes first female presidential nominee. Okay? So remember this one. We are going to get back to this. And this is actually not true by certain standard. So essentially, Maverick is about finding things fascinating and interesting to say about entities in a knowledge graph. And because of that, we believe this system can be useful in supporting or enabling a few applications, including fact-checking and fact-finding. Fact-finding, obviously, right? So it is about finding facts. And fact-checking, suppose you have heard of a factual claim, or you read about a factual claim, and you run your algorithm. You use Maverick system over your data set, and you identify a claim that you can make which is inconsistent with the claim you just heard, right? So that may suggest that you just heard a false claim. So on the other hand, the system can be also useful in data cleaning, right? Because it could be that the claim you heard or you have seen is actually true, and the fact you discover using your algorithm is wrong because your data has some quality issue, right? We all know there are missing links, and there are missing entities in a knowledge graph, or even wrong edges, and so on. And this can be useful in a recommendation system as well, because Maverick essentially is about recommending objects, friends, products, and so on. So here is a screenshot, a snapshot of a screenshot from Google search results. Right? So if you search for Willis Tower in Chicago, you may see this info box. And at the bottom of the info box, you see this "Did you know" feature. And it says Willis Tower in Chicago is the second tallest building in the US. right? And if you think about it, this actually matches our definition of exceptional facts exactly. Right? So I'm not saying Google necessarily runs an algorithm like Maverick to find such kind of facts, because there are many other ways, information extraction and so on. Right? But potentially, an algorithm like Maverick could be useful in enabling features like this. So let's look at a more concrete example, this toy, tiny knowledge graph about World Cup. And then we see three kinds of entities in this graph. Right? We see goals in ovals, we see players in rectangles, and then we see teams in triangles. Okay? So let's say we are wondering what is exceptional about G1, right? So this is one of the goals in World Cup history. The way we model the problem is that, remember the goal of Maverick is to find a context and a subspace such that we can make an entity of interest stand out, right? So we need to model both the context and the subspace. So the subspace is a set of attributes, and attributes, obviously, we can define them by essentially, incoming, outgoing edges of a node, right? So in this case, G1 has an attribute which is awarded to, and its value on this attribute is Croatia. Of course, it has other attributes as well, scored by S1. So how do we model context? Context defines a set of entities sharing some common characteristics, right? So this is defined in our way. We define it by a pattern and a variable pair, right? So here you see a very simple pattern, 3 nodes, 2 edges. G is a variable, and S is another variable, and Brazil is a instance of an entity, right? So this defines all the goals scored by Brazilian players. Okay, and we highlight G because G is the variable we consider here, and all the matches to this pattern, and the corresponding nodes that are matched to this variable G, they form the context. Okay, and this G1 is part of the context. And this context has 3 entities, G1, G2, G3. These are all the goals scored by Brazilian players. So what's so interesting about G1? In these 3 goals, among all the goals scored by Brazilian players, this is the only on goal, because this goal was awarded to Croatia instead of Brazil, right? Both G2 and G3, they were awarded to Brazil. Right? So that is what is exceptional about G1, and that is what our algorithm, our system, aims to find. So a little more formal definition of the problem. We are given an entity of interest, V0, and we are given an exceptionality function, X. Essentially, this function helps us to define what is interesting, what is less interesting, right? And a result size K, and our goal is to find the top K pairs of context and subspace with regard to this exceptionality function, such that this entity of interest, V0, stands out, okay? And clearly, you can quickly see, all these different challenges, based on this problem definition. Apparently, the number of subspaces for attributes is very large, exceptional, right? Number of patterns, in other words, number of context, is also exceptional, right? So here we are just listing, on the left-hand side, all the possible attribute subspace, okay? If you're familiar with how we model a data cube, then you are familiar with this lattice structure of different subspaces. Starting from an empty node, and then we have one attribute node, which had, including score by, awarded to, and a match, and then we have 2 attribute nodes, scored by, awarded to, scored by, match, and so on. So one clarification I need to give you is that we are not considering all possible ways of defining attributes or subspaces. Right? We are limiting ourselves to conjunctive star queries. Right? So think about an entity, and all the edges are either incoming edges or outgoing edges of that entity. Okay? And a subspace is a subset of these edges. We do not consider edges 2 hops away or 3 hops away when we define the subspace. Okay? So the right-hand side of this slide enumerate all the patterns that we consider in this example. So when we define the patterns or context, we actually allow more general forms of graph pattern queries. Okay? So in this example, you see paths and so on, but in general, it can be a subgraph. Okay? Of course, we have to limit ourselves to certain size of patterns. So in our experiments and so on, we will allow a pattern to have at most a handful of edges. Okay? It's because in practice, if your pattern has 10 edges, 20 edges, the fact will not be interesting anymore. So let me just briefly mention things that have been done in the past related to this project. And outlier detection obviously is relevant. The difference is that the goal of Maverick is to find conditions that make an entity or make an object stand out, even though that object may not necessarily be an outlier, right? So in other words, if I look at people in this room, and my goal is for each one of you, I want to find something to make you appear interesting and fascinating so that I can introduce you to other conference attendees. And it will not be so realistic to say all of you are outliers, right? Otherwise, it's meaningless to define outliers. So that's the difference. There are also another line of work on outlying aspect mining. This was mainly done on relational tables, and mostly on a single table, right? So we could adopt existing algorithms on finding outlying aspects of relational tuples. But then the challenge there is we'll have to assume a single table model. And if we want, we can use a single table to model a graph, and we will end up with a huge, very wide table with a lot of sparse cells, with a lot of empty cells. Right? So another challenge is that if we don't use the single table model, if we use multiple models, then we'll need to adopt existing algorithms to handle joins, right? And it's not clear how to adopt those algorithms because they were designed for single models. And there are challenges like how, with regard to how to handle set values, because due to the heterogeneity of graph data, an entity's attribute, its value oftentimes has a set of values, right? Someone has attended not just one conference, but 10 conferences in the past. So that attribute has 10 values as a set. And the current algorithms were not designed to deal with it. So here's the architecture of our system, Maverick. If you think about our goal is find the pairs of contexts and subspace of attributes. So you can view this as nested loops. So the outer loop enumerates all the patterns, all the contexts, okay? And so, so this space of all the patterns is very large. We organize it as a pattern search tree based on the subfunction relationship between these different patterns. And then instead of using breadth-first search or depth-first search, we use a beam search strategy. So In beam search, at each level of the tree, we maintain a beam, which is basically a small number of patterns that we feel or we believe are promising. Okay, so basically at each level, we select, let's say, the 2 best, most promising patterns. And then for each pattern, we'll use this context evaluator to find all the matches to the query pattern and the corresponding context. So in this, we can use any existing graph query system. And then for each context, this exceptionality evaluator will use a structure called set enumeration tree to basically enumerate all the, the space of attribute subspaces. And of course, once again, the space is very large, and we cannot afford exhaustively enumerating it, so we have to use some strategy to prune it. Okay? So the pruning of that set enumeration tree is based on some upper bound upper bound properties of different exceptionality functions. So I'll skip the details so you can find how we define these different exceptionality functions in the paper and how we derive the upper bounds. Okay. And then I want to say a few more words about how we generate patterns. Okay. So this space of patterns is very large. And first, we adopt a few rules to make sure we do not waste time on useless patterns. So what are useless patterns? Let me give you one example. Right. So if a pattern doesn't have any match, then you will end up wasting time enumerating that pattern and evaluate that pattern and not finding anything. So that's our first rule. Do not consider any pattern that doesn't have match or doesn't define a context for the entity of interest. The second rule is that when we grow a child pattern to a parent pattern, right? So this child pattern, in this case, let's say P1, and the parent pattern is P5, we make sure the newly added edge involves at least one attribute. So for that reason, P5 is a pattern that we want to skip. Why? Because this newly added edge from S1 to Brazil, right, which basically says, this player plays for Brazil, right? So if I intuitively explain the idea here, let me go back to the earlier motivating example. Right, so basically we'll be saying things like, among all the goals scored by Brazilian players, this is the only own goal. By the way, Brazil has a population of, I don't know, certain figure, right? So that, by the way, is irrelevant to why this entity stands out. Right? That's what we want to exclude. And then we also remember the other rule that we said is that we want to avoid evaluating patterns that do not return any context, do not have any match. So our algorithm uses this way of, we call it match-based pattern generation. Essentially, when we grow a pattern P9 to P11, we first will evaluate pattern P9 to get all the matches M9. And then, so basically that's a subgraph in the data graph. And then we find all the supergraphs of M9. For instance, F10, and then we find the corresponding query pattern, P11. That way we guarantee P11 will end up getting some context instead of returning empty results. So the details about these can be found in the paper. Let me just show you one figure from the results, from the experiments. So here we are comparing several different search strategies of our search space of patterns. And this one, called beam convergence, is the one that we are advocating for, right? And we actually did the same experiments on different kinds of exceptionality functions. So this function is one of the 3 we consider. And what you can see is that if we run the algorithm for a while, this strategy will find more interesting facts because they have high scores, okay, and constantly. And other strategies, they'll find only a few, and most of the facts have very low scores, and they do not constantly yield, okay? And of course, there are more experiment results in the paper, including user study. The paper also provides a list of sample facts that we found from Freebase. We have a demo in VRDB, so if you are coming to VRDB this year, please visit our demo in the conference. And that concludes the talk. Thank you very much.
Hi, this is very interesting idea. I guess my question is how much we rely on the complexity of the functions, exceptional functions that are defined. So first, how many such functions you can handle at the same time, or do you have to handle them one by one? And the second, how many types and different types and edges you could afford to run all of this? Like in your experiments, you have like hundreds to thousands of types, but in real knowledge graph, you have tens to hundreds of thousands of types and edges.
Yeah, thanks, Luna, for the excellent question. So I guess there are two questions. The first one is about the exceptionality function, right? First of all, the framework itself is agnostic to the choice of the exceptionality function. So in other words, in principle, it can allow any function, right? And as long as you are able to derive a upper bound based on that function. But of course, in principle, once again, in principle, given any function, you can always come up with upper bound. It's just a matter of whether that bound is tight or not, right? So if it is too loose, then it doesn't have any pruning power. In the paper, we consider three exceptionality functions. One of them, they are all quite intuitive. For instance, one of them is called one of the few, which is exactly what that Brazilian goals, is about. And then another one is slightly more complex. It considers not only whether something is unique, but also whether you can also say other, unique things about other objects. Right? To some extent, I can perhaps say something unique about every person in this room. And if all those facts are interesting, then you don't really stand out. So that's the idea of the other scoring function. I don't know if this is a little off topic. Does this answer your question about the exceptionality function?
Partially. How many in total? How many in total?
So in the experiment, we consider three. Yeah, but we don't really put them together. So it's like we do experiments using this function. We do another set of experiments using another function. It's not like in our system we consider multiple functions at the same time. Yeah. So the second question is about efficiency and whether this is able to handle real large-scale knowledge graph. So that's a very valid question. If you look at the experiment setup, you notice that we are not running this over the whole knowledge graph, Freebase, exactly because it is too much for the algorithm at this moment. So we handle, for instance, VM award is a set of Freebase. It has 95 different node types and 100 edge types. It is still very large, 5 million nodes and 10 million edges. But obviously, this is much smaller than Freebase itself. So even on this small graph, the algorithm is still quite costly. Even consider that we apply all these pruning strategies, heuristics, and so on. So we actually have a live demo. And so in the live demo, online demo, you can enter an entity. The system will return all different facts. But it takes quite a while for the system to even generate facts about one entity. So in the experiment, we actually just run the algorithm for, say, 2 minutes, several minutes, see what we can produce. And ideally, let's say if we can deploy this in Amazon using a huge cluster, then what we are going to do is to keep this running for a whole year and see what kind of effects we can produce, right? So, and apparently we have challenge in doing that. If you can support us in doing that at our university, that would be great. Yeah. So I hope this answers your question.
Okay, thanks for the answers.
So there were two interesting examples on the slides. The second black, the second black were winning the best actor award and the second tallest building. So my question is about this number 2. Is it like an upper bound to be exceptional, or is it the coincidence that of these two examples, or it's just a hard-coded rule that the system uses to extract this type of facts?
Mm-hmm. So I'm not sure if I exactly get the question, but let me try to respond to that. I think the question is, so we're looking at the first example, right? And the first example says Denzel Washington is only in the second black. So how do we come up with the second, or why do we insist on finding whether someone is the second? Is that the question?
Yeah, and also the second is the interesting example on a different slide, is about the second tallest building, right?
The second what?
The second tallest building.
Oh, okay.
So
yeah.
my question is basically, is it like an upper bound to be exceptional? If I'm a third, I'm no longer exceptional, for example, right?
Oh, no. So,
or it's maybe a coincidence, or just...
This is, the fact that you see second twice in these two examples is a total coincidence. So keep in mind, first I need to clarify, the outcome of our system are not natural language description of these facts. Although we promise that we will have that sort of in our real DB demo. We are working on that day and night. So, but we generate context subspace pair, and for each pair we come up with a score. That's basically what we generate. So the exceptionality function determines what will be the outcome. And then we need to interpret that outcome. So that outcome could be the third black or even the 100th black to win a certain award. Yeah.
So it is basically up to the user to define
the function.
Exceptionality function. Right?
That's right. So that itself is not so easy. Yeah. So that's another place where you can do things to improve the system.
Okay, just very quick question. Okay.
Okay. I'll address your question offline. Thanks. Oh, sorry.